The question that I have is, could you give us some examples where equilibrium of a particle is involved? Let's first recall the definition of a particle. A particle is one whose dimensions can be neglected in the analysis. Supposing, say, I have a rigid body, like a steel ball or a pulley that is made out of steel. Say this rigid body is subjected to multiple linear forces, like in this example, I have F1, F2, and F3 acting on this body. Let's further assume that lines of action of these forces, which are these, right, they all meet at a single common point. And in this example, this is point A. So it turns out, in the analysis of this rigid body, I can ignore its dimension and approximate this rigid body by a particle whose spatial location is point A. Therefore, a particle is represented by a point in the analysis. This is a rigid body and therefore there is no internal deformation. In other words, one point inside the body does not move relative to another point. So a steel ball, for example, can be approximated into a rigid body, but not a tennis ball or a soccer ball. The body is not subjected to moments or torques, which we will define and analyze in the next chapter. When these forces don't meet at a common point, like in this example, then these quantities, moments and torques, begin to show up. They need to be considered in the analysis. This is exactly what we will do in the next chapter. But for now, we're going to assume this to be a particle, and all of the forces acting on that particle meet at a common point. So there are several real-world examples that fit this framework of approximations, and let's look at some of them. Here's a simple example where a mass of 50 kilograms is being hung in space by this cable system. There are three cables involved, this vertical cable and then these two inclined cables. The inclined cables are being attached to fixed supports, this one and this one. These are cables, so they are capable of carrying tensions but not compression. All three cables are tied to this rigid ring. Here's an exaggerated picture of the ring along with the forces acting on them. There will be a tension in each of the three cables. T1 is the tension in this cable, T2 is the tension in this cable, and T3 is the tension in this vertical cable. The line of action of the force representing the tension is in the direction of the cable. At equilibrium, we can prove that if we extend the lines of action of these forces, they all will meet at a single common point. This common point is point A in this example. If I am considering the equilibrium of this ring, we will approximate the ring by a particle like in this picture here. So this is exactly what we will do in solving this problem. In other words, in finding the tensions in these cables, which we will take upon in the subsequent videos. Here's another example that involves a frictionless pulley. It's pretty common to use pulleys in cable systems, right? Usually there will be a little bit of friction between the cables or the ropes that go around the pulleys. But in this course, we will neglect that and assume that the pulleys are frictionless. So what does it exactly mean? Well, it means that the tension in the cable on either side of the pulley is the same. In other words, T1 and T2 are equal to each other. Pulleys are made of metals and therefore they can be assumed to be rigid bodies. Let's say this pulley is being held on a fixed point, fixed support by an arrangement shown here. So here we have a link that connects the center of the pulley to the fixed point. Usually these connections are hinges. Let's say the force on this link is F. It turns out that if these are hinges, the line of action of this force is going to be in the direction of the link from A to B. You can then prove that these three forces acting on this pulley, T1, T2, and F, will meet at a common point B. This common point doesn't always have to be inside the rigid body. It could be outside, like in this example. In fact, consider an extreme case where these two cables are parallel to each other. Then the force on this link is going to be vertically up, like this. So then, where do the three forces meet? T1, T2, and F. Where do they meet? Because they are parallel to each other, right? So where do they meet? Theoretically, you can think of them as meeting in infinity. So a particle subjected to a system of parallel forces is an acceptable system. It can be in equilibrium. The forces in such a system don't have to meet at a finite point. However, as soon as the force system becomes non-parallel, they all have to meet at a common finite point. Here's another simple system where a rigid body is being held on a slope by a cable. The tension in the cable is T. The body has a weight which is going to be acting vertically down at the centroid of that body. Let's assume that the slope is perfectly smooth, then there will be no shear force between the body and the slope. But there will be a normal reaction. Let's call that as N. So the line of action of N is perpendicular to the slope. Then the three forces, N, W, and T, will meet at a common point A. Therefore, this rigid body can be approximated by a particle whose spatial location is point A. And these are the forces acting on that particle.